So I want to go over the theory of the assignment that you did last class, which, by the way, I've submitted the, please don't go and look at it now, but I've submitted your comments back onto Moodle so you can go and check them out later. Not right now. Essentially, there's no grade on it because if you did it, you got full marks. If you didn't do it, you got no marks. Okay. Um, there is quite a bit of theory behind it, though. I said not to look at it now. You guys are okay with that? Yeah? Okay. The theory behind it is quite important because it's part of circuits and understanding how circuits work. So we're going to talk about that today. So this is the theory following the assignment that you guys just did. And we're going to talk about voltages in series and voltages in parallel, because the next part of the course, we're going to assume that there are multiple power sources in a circuit. Okay, so as you guys know, actually maybe you don't know, who here has seen inside of a computer before? Yeah, a little bit. You guys notice that on the motherboard there's like another like a little watch battery? Yeah. So that is, I mean, it serves a purpose. It's to keep the clock of the motherboard going and all that. But the point is that when you're running your computer, there is that battery that's doing something. There's a voltage of your entire I think that's plugged into the wall. That's doing something. So you have multiple power sources and controlling the same thing. And so we need to be able to look at circuits that have multiple power sources. So the first and most simple example of this would be if the batteries were in series, and here it says very simply, the voltages, they add up, okay? So if this is three 1.2 volt batteries, then in total, the voltage for this is going to be 3.6 volts. And one thing that when I was looking at your papers, I thought was a little bit misunderstood is what does it mean, the battery's longevity? All right, longevity normally would be measured in what? If I were to ask you, what is your longevity? What is the typical human's longevity? You would say 80 years old. Okay, that's the average life expectancy of an adult male or female. Now, I think that's pretty good. It used to be 77, maybe 5 years ago, but it's around that ballpark. And it's measured in what? You guys gave me that number, and the units were years, which is what? Time. So if I ask you for the longevity of a battery, you're going to give it to me in time, all right? It's going to be a time. The longevity of the battery is in time. And obviously, if you ask of it more tasks, then it's going to take less time. And if you ask of it very little tasks, then it's going to take more time, right? And a lot of you talked about this thing called capacity, but that's not a very accurate term. And I probably made this comment in every one of your papers. Battery's capacity is not actually an electricity and magnetism term. Capacity is reserved for the term capacitors, which now you guys know what it is. You're doing a lab on it. The capacity of a capacitor is how much charge a capacitor can hold. And a battery is not really typically described as having a capacity. It's typically described as having a charge, right? And then when that charge runs out, or how long it takes for that charge to run out, is what describes its longevity, right? So we're going to talk about what the longevity or how the longevity works for having a battery in series. But before I do that, I just want to prime you guys. Nope, not positive Q. We're going to call this negative Q. We're going to say that this battery has negative Q, this battery has negative Q, and this battery has negative Q. So in total, the amount of Q available is how many in this case? Minus 3Q. So in total, you have minus 3Q charge in these three batteries in series. And that's going to be important later when I do some calculations. So just remember this, please. Okay, I'll come back to it. Any questions? So cells and batteries, those terms are synonymous. You can use them interchangeably. So batteries can be also wired in parallel, as you can see here, and you guys will have to do that. And in this case, the voltage remains constant. Okay, so if I have three 1.5 volt batteries, this one's 1.5 volts, this one's 1.5 volts, and this one's 1.5 volts, the voltage of the source, the total voltage for this circuit is going to be, yeah, 1.5 volts. By the way, because you guys are the first class out of the three that this lesson is being given to you, also just decided what's going to happen for the other two classes. You guys have that power. Some people get a high on it. Okay, so let's do some calculations. I have a circuit here that's 5 volts, right? And 20 amp light bulb that's lighting it up, all right? Could you guys tell me what is the current passing through that light bulb? If we were to just do a quick calculation. So V is equal to I times R. 0 0.4, is it? 5 divided, 0.25. So 0.25 amps. That means that this lamp is getting 0.25 amps going into it. Okay, we have no idea how much is leaving the battery. All we know is that 0.25 amps are entering the resistor, that's entering the light bulb. Okay, that's what we calculated. But now we have to follow the current backwards to see what's the source. Oh, okay, so it's coming from this battery. And before that, everything was in series. So that means that the currents coming out of the battery had to also have been 0.25 amps. Okay? Now, if the voltage doesn't change, actually, before I do that, let's talk about the brightness of the bulb in the first picture. So if I talk about brightness, brightness is another term for power, and power is equal to I times V. If you say your brother just fell on the floor. You okay with that? Okay. So power is equal to I times V, and power is the brightness. In this case, it would be the current, so 0.25 amps, multiplied by the total voltage, which is 5 volts. That equals to how much? 1.25, and the units for power is watts. Okay. You might also see much bigger things. You might see power expressed as horsepower. That's that's mostly for motors, and it describes basically how much torque they can generate. Yeah. Yeah. Lumens. Okay, yeah. That's a standardized brightness scale. Kind of like you can say like, are you into like spicy food? Okay, so like you can measure spicy food in what's it called? The what? Scoville index. It's kind of like that. All right, it's arbitrary and it describes how spicy something is. Lumens are arbitrary and describes how bright something is. I think there might be, but I wouldn't know. I wouldn't know. There might be some standardized part of it. Okay, perfect. So the brightness here is 1.25 watts. All right, not very bright, but okay, let's move on. And let's do the same calculations for the second one. What's the voltage on this circuit in the second parallel circuit here? So much? 5. So the voltage again is 5, right? And the voltage is equal to I times R, and R is 20, so I times 20 ohms. And therefore, I is equal to, the multiplication sign, I is going to be equal to the same thing, 0.25 amps. That means that there is 0.25 amps coming into that new light bulb. Okay? 0.25 amps are coming into this light bulb here. But this 0.25 amps, it came from a junction, and that's strange. Let me just erase this. Okay. So this is coming from a junction, and at this junction, there were two currents that had to combine to give you that 0.25 amp that you got for the bulb. All right. So there's a current, we're going to call this current 1, and we're going to call this current 2, right? And we can say that current 1 plus current 2 is going to be equal to 0.25 amps. And logic states that if two numbers, when you add them up together to give 0.25, then those two numbers have to be a number below 0.25. So in this case, you can see that the amperage leaving each battery is less compared to the first situation where the amperage is going to be the same, right? And I want you to remember, because I'm going to talk about this later, that each of these have a charge, I wrote positive, but I mean negative. Each of these batteries has a charge negative Q. Okay? Again, I'll come back to that later. And if we calculate the power of this second bulb, well, it's the same thing. Power is equal to 1.25 watts. So did the brightness change? No, it did not change. What changed between situation 1 and situation 2? Well, we don't know about longevity yet, but talk to me about what we do know, what I did calculate here. Yeah? Yeah, the current coming out of each cell is going to be lower than if there were just one battery, okay? And we still haven't connected how current is related to longevity yet, okay? We're going to get to that then. What's the total charge of the first battery here? What's the total charge here? Here it's going to be minus Q. What's the total charge here? Minus 2Q. All right, let's move on. Let's do the same thing in series. I'm just going to write down the charges real quick. So that's negative Q. This one's going to be negative 2Q again because it's two batteries with 2 times more charge available to do work. And I'm not going to rewrite this, but we know that the current here is 0.25 amps. We know the power here is 1.25 watts. It's the same situation as what we just did, right, in the previous page. And now here, what's the voltage of this new power source if they're in series? I didn't hear you, Melanie, so I'm going to go with Shani. 10 volts. You can speak louder, it's okay. So voltage is going to be 10 volts. The resistance is 20 amps. And if I did V is equal to IR, I can say that I is equal to 0.5 amps. Good. And if I is equal to 0.5 amps, the power is going to be equal to 0.5 times 10, and that's 5 watts. How many times more bright did adding that second battery in series make that light bulb? 4 times more bright. So if I were to talk about the brightness increase, I would do a ratio of P2 divided by P1, which is 5 watts divided by 1.25 watts. That equals to 4. So I can say that I got 4 times more brightness from adding one battery of equal strength in series to the circuit. So what's the relationship between voltage and power? Or maybe I should say, no, forget that question at all. Don't answer. It's a bad question. You got 4 times more bright. That's what's important. So we said that the current coming into this resistor is 0.5 amps. And this is where longevity comes into play. If 0.5 amps is entering the light bulb, and this is a series, and we assume that Kirchhoff's law is true, which of course it is, otherwise why would it be a law? That means what about the current that goes through this series circuit? Yeah, it's always the same. That means this battery is getting 0.5 amps. This battery is getting 0.5 amps. or drawing is being drawn from it. 0.5 amps is being drawn from it. And what about this battery in the first circuit, just out of curiosity? What's going to be the current coming out of that? 0.25. All right. Now, I'm going to just add an extra slide here so that I can show you guys my calculations. All right, so here I'm going to talk about longevity. And what we need to understand is what current means. What is the definition of current? Yeah. The rate at which, well, you're using current in current's definition, the rate at which charge flows. Yeah, exactly. So it's a rate of charge. So it's coulombs per second. Whoop. It would be charge per time. Or if I were to look at the units, it would be coulombs per second. Right? And I don't know if you guys notice this. If any of you guys are like telephone or like cell phone people that look into like cell phone reviews and which cell phone is the best, and you like looking at the specs and things like that, a lot of their batteries are, the battery life is measured in what unit? Not par, fois, milliamp hours, all right? And just so you know that, let's just write it down here, milliamp hour. That's really just a unit for current multiplied by a unit for time. And if I just reorganize this equation here, I get that unit multiplied by time is equal to charge. Right? Right? That's okay. I think we're missing one other person, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17. Who am I missing? Amanda. Okay. Okay, yeah. So current times time is equal to the charge, and so it makes sense that we measure battery and how much charge they have. That's not what I just told you guys, right? So milliamp. If something has 300, normally a cell phone is going to have something like 3,300 milliamp hour, and that's describing how much charge a fully charged battery of this cell phone can hold. The more charge it has, the more things that it can do, right? All right, so perfect. Let's talk about longevity of those batteries now. So we said that if I had a battery in series, and this is Q, and I compared that to parallel, which has 2Q, 2Q, or two batteries in series, a charge of 2Q, right? What was the current, and we're always going to go back to the same example, what was the current coming out of this battery to go into this bulb? Do you guys remember that? You just go back and tell me what you guys were done. 0.25 amps. What about for this one? We said it was some number that when you add together, it gives you 0.25. So if we're going to assume that they're equal, we can assume that each one is 0.25 amps. 0.125 amps, rather. And here we said that the current coming out of the battery is what? The current, not the voltage. What was the current? 0.5 amps. Okay, so the charge was 2Q. So again, I'm just going to write the equation down. I is equal to Q over time, right? The charge here is just Q. We're looking for time, and the current is 0.25 amps. That's for the first one. For the second one, if we're looking at the longevity of each battery, the current coming out of each battery is 0.125 amps. Oh my goodness. is equal to 2Q over time. And here it's going to be 0.5 amps is equal to 2Q over time. So in these situations, which one's going to have the longest time? So just out of, for argument's sake, we're going to give Q a number so that we can compare. So we're going to say that 1Q, let's call that 100 or 1 coulomb. And we're going to call this one 2 coulombs and this one 2 coulombs. Which one is going to have a lowest or highest time? So if I isolate T here, T is going to be equal to 2 divided by 0.5. It's going to be 4 seconds, let's say. Here, 2 divided by 0.125 is going to be 8 seconds. And here it's going to be 1 divided by 0.25, and that's going to be how long? 4 seconds. So what could you say about the longevity of my battery? Which one? You're right. You're right. So I have 4 seconds in the first situation, 16 seconds in the second situation, and 4 seconds again in my last situation. The longest battery life is going to be obviously this one. This is what your research showed you on your assignment. Right, but now we can quantifiably say that this one is going to have 4 times more longevity than if you were to use just one battery in just one battery or 2 batteries in series. What is it doing? I think my PowerPoint just crashed. Oh, no, there we go. So this one has 4 times more compared to this and this. So what's more intelligent, to use the 2 batteries in parallel, or is it more intelligent to use 1 battery at a time? Because some of you wrote that in your answers. You wrote that maybe it's better to use just 1 battery, wait till it dies off, and then use the second battery. What's better? Yeah. Exactly, right? And the brightness doesn't change. Between this situation and this situation, the brightness doesn't change, right? But by having them in parallel, you'll have the same exact brightness lasting 4 times as long for only twice as much battery, all right? So the most, if you wanted to go for longevity, the best thing to do would be to use 2 parallel batteries. Okay? Does that make sense? Yeah. So here it talks about brightness. So more power equals more brightness. I talked to you guys about this. And we did this already. We calculated I for this. We calculated I and P for this. I didn't realize that I have more space for this here. So what's going to happen if I add more lamps here? So let's say I added another current, another bulb here of 3 ohms. What's going to happen to the situation? Yeah. The resistance will increase, so let's figure it out. Resistance is equal to 1 over 3 plus 1 over 3 is equal to 2 over 3 power of -1, which is going to be equal to 1.5 ohms, right? No? Yeah. Is this not on there? I added this slide later, but I thought I uploaded it before. No? Keep going, keep scrolling down. There, that one. You guys have it? No, it should be there. I see it on you guys' slide. Could you scroll down? Oh, yeah, I did, yeah. So as more lamps are added in parallel, what happens to the brightness of lamps? Okay, so now we know that the resistance is 1.5. And now we can figure out what the current is. So the voltage is equal to I times R. And the current is going to be, so 1.5 volts is equal to I times 1.5 ohms. Therefore, I is going to be equal to 1 amp. Okay. That means that the total draw from the battery is 1 amp. And because these 2 resistors are equal, what is each resistor getting? What current is each resistor getting? Hello. So the resistor is going, the current's going to split at this junction here. Remember, Kirchhoff's law. Current splits at a junction. So if this is if this is 1 amp going in, and there are two equal resistors, what is the current going in each direction? Yes, 0.5 amps. 0.5. And so now we can calculate the power of each. And power, we learned that it's IV, but it's also IR squared. So 9 times I is 4.5 watts. And here it's going to be 4.5 watts. Yeah, Johnny. Oh, I squared R, you're right. I squared R. I made a mistake. I squared R. So therefore is 0.25 times 3. So that's going to be 3 divided by 4 is 0.75 watts. All right. So this is what the brightness of the bulb is if you put them in parallel. Could you guys just go back and do that same calculation? Tell me what the brightness is going to be with just one battery, one bulb, one 3-ohm bulb. Like when I had nothing drawn here, what would be the situation? What would be my wattage? You guys work on that. I'm going to do it here. Let's just make sure we get the same answer. So judging by our calculations, I hope you guys got the same thing as me. It's 0.75 watts if there was just only one bulb or two bulbs or X bulbs. The power of each bulb is going to be the same, and therefore the brightness is going to be the same. Now in this case, the current leaving the battery was 0.5 amps, and when you had two bulbs, the current leaving the battery was 1 amp. All right, so okay, so let's answer my questions now. One, as more and more lamps are added to parallel, what happens to the brightness of the lamp? What is the answer? Stays the same. I'm glad I only have 1 or 2 students in class today. Everyone else, please speak up. But if you have more bulbs, your resistance goes down and down and down, and therefore the current goes up and up and up. So look at the current in this one. So 2 bulbs, the current is 1 amp. 1 bulb, the current is 0.5 amps. Right? That's the current leaving the battery. Okay? Stays constant for the brightness. 2, as more lamps are added in parallel, what happens to the current leaving the cell? It's what? Yes, increases. As more and more lamps are added in parallel, what happens to the longevity of the cell? The longevity increases. So it lasts longer, the battery. So why wouldn't we just always have everything in parallel? Not only does it get everything to be just working just fine, but it also lasts longer. Can't do that. Something has to be a compromise. So in this case, the compromise is decreases the longevity. Okay. Now imagine that this battery had a charge Q, right? If I'm asking for it 1 amp per second, so 1 current per second, 1 coulomb per second, versus if I ask for it 0.5 coulombs per second, what's going to last longer? When I ask for it 1 coulomb per second or 0.5 coulombs per second? Yeah, it's going to last longer if I ask for it 0.5 coulombs per second. So of course the longevity decreases as I add more demand on my circuit. You guys do this one? So here we have 2 batteries, we're adding more lamps. We're not adding more batteries, we're adding more lamps. But just on all those situations, there's going to be 1 more battery to consider now. You can, we'll start with one, doing the calculations for 1 and then add a second one and see what happens. So if you were to follow what I did here, I calculated what would happen if I only had one bulb, and if I had one bulb, it would be a current of 0.25 amps. And since that current is coming from two batteries, then each battery is providing 0.125 amps. However, if I have two batteries, two batteries and two bulbs, the current going into the bulb section is going to be 0.5 amps. And therefore, each battery will be using 0.25 amps to power these two batteries, and each bulb will be getting 0.25 amps. And therefore, the brightness doesn't change compared to if there were just one battery, one bulb, but the longevity of the batteries increase and you're powering more bulbs, right? So if I were to compare two batteries, two bulbs, to one battery, one bulb, it's pretty much the same. Now, of course, wires have an internal resistance. So this is just theoretical values. The more wires that you use, the more inaccurate your calculations are going to be, because wires don't very efficient. Well, they are very efficient, but they're not 100% efficient at transferring a charge. Okay, so they do heat up, and you do lose some current from just having a current going through a wire. Okay, let's get a bit more complicated now. This is what you guys are going to do. So you're going to have do this problem. Just do this problem. All right. And after that, we'll take a break, and then we'll do the activities. Okay. So this is it. Work on this. I'll be working out on the answers in the front. If you have any questions, just come and ask me. Okay. Yeah. Oh, I didn't put one in. I'll do that today. Thanks for telling me. So a closed switch means that it's going to be in this position here, okay? That's what a closed switch means. An open switch is no current is going to be here, so this is going to be open. And a closed switch means you actually close the switch and you're completing the circuit. You're done? You want to go to the next one? You want to do the next one? Yeah. Oh, okay. Sure. If you're done working on this, take a break, come back at 10:35. Then we'll continue from there. If you really want more practice, go to the next problem. You can work on that one. The axis doesn't change. And you leave the linear axis for your data point. Yeah, it's totally fine. For the graph, could you go back? Could you just make one curve for the average? Leave the other ones as data points. So here you have three curves. I just want one because you have, what is, why are there three? It's for your three travels, right? Oh, I see. Okay. So you don't need the experimental one. You put the points for experimental, but not one. In a graph, you can never put dots and connect the dots. You're not allowed to do that ever in Science. Yeah. Each tool means closed. The S one is closed. Okay, so now this is closed and this is closed, so everything is activated kind of thing, right? And so you have to calculate the equivalent resistance of these three. That's what I did. These two together is going to be 1.5. And they're going to be in the case where total resistance of 4.5. Voltage is 5. And then you can find the total current. Total current is 1.11. Okay? So that's the total current. When the two values are joined together, that point is going to be 1 amp. So what those do the first law, they're all 1.11 amps, so those do the first law. And here it gets split evenly because of equal resistances, so they can shift 0.5. If you were to compare that to if this switch was open, this one was getting, according to this, 0.25 amps, and this one is also getting 0.25. So this one's getting a lot more, this one's getting more, but it's not as much. Pretty obvious. Yeah. That's for 5 times 0.25 should be 0.125. 0.25 times 0.25. So a quarter of a quarter is 1/16. So you're right. I'm wrong. It's 0.065. Not 0.65. 0.065. Yeah, you're right. Where's the voltage right? You're right. That changes everything. Okay, so it's 1.5. Okay, so all this is wrong now. So what's going to be the current now? Yeah, you're right. 0.33 amps. And therefore, this one here is 0.33 amps. And this one here goes to half of that. 0.33 amps is going to be 0.166 amps. 1.166. Is this what you got? And so therefore the brightness for 1 gets brighter and 2 gets dimmer. Yeah. Dimmer. So you guys were asking me about this, and I made a mistake. I had used 5 volts here instead of 1.5 volts. Take a look at the new answers. I had made a mistake before, so just take a look, make sure you still understand what I'm doing. Yep. No, because it's not the same. You should be able to find it. Keep looking. Yeah, if not, find someone else and see what I've got. You should be able to find it. Determine a trending line. Is it the trending line or is it the line that has the highest? Yeah, you said you should have all of your data here. Yeah, so you have the trending line should be for your average, but all your data points should be on it. 100 is 1 sig fig. Yeah. 100 point is 3 sig figs. Yep. No, that's fine. You can compare it. As long as it's clear. I also put up the answers for the problem afterwards. In the discussion. Is that your dog, Mark? Is that your dog? It was? Oh, he passed away? Oh, I'm sorry. Recently? Okay. What was his name? What's his name? Manny? Okay. Do you have another one now? Okay. It's harder, yeah. Yeah. Yep. Okay. Outside. Got it. I got breaded. Yeah, I haven't put up the link yet.
That's it. That's why I'm
Yeah, I'm gonna do it while you guys are doing the activity. I'll do it.